Okay, now I'll be going in depth into the how do you actually prove these formulas. Okay, so hopefully if you cannot remember the formulas in the exams, you will be able to derive them on your own. Okay, using just some logical steps. Alright. So let's look at the first formula. If I have a to the power of m times a to the power of n, you give me a to the power m plus n. How do I derive that? Okay, so let me just give you an example. If I have 2 to the power of 3 times 2 to the power of 2, take note that it's the same base, okay, of 2 and 2. Okay, if I split them up into their respective what this power of 3 actually means, it actually means 2 multiplied by itself 3 times, so it's 2 times 2 times 2. Okay, and because here is a times, so multiplied by, so 2 square will be 2 times 2. It will actually just be, if I do the multiplication, I take away the brackets, it will just be 2 times 2 times 2 times 2 times 2, right, which is the same as 2 to the power of 5. Okay, so what I have is 2 to the power of 5 is the answer. Okay, and 2 to the power of 5 is actually 2 to the power of 3 plus 2. Okay, so 2 to the power of 3 times 2 to the power of 2 is the same as 2 to the power of 3 plus 2. That will give me 2 to the power of 5. Okay, so it's proven. What about for the second one? Okay, am divided by an equals to a to the power of m minus n. Okay, so once again, I will use same base. Okay, in this case I'll use 5 to the power of 3 divided by 5 to the power of 2. Okay, because it is a divide, so in this case it will be expressed in form of fraction, whereby the numerator will be 5 to the power of 3. Okay, 5 times 5 times 5. Denominator will be divided by 5 squared, so it's 5 times 5. Okay, the 5's will cancel out. Okay, this 5 times 5 will cancel out with the denominator, so I'm left with 5 to the power 1. Okay, and I can see that this 5 to the power 1 here, this 1 is obtained by having 3 minus 2, right? So 5 to the power 3 divided by 5 to the power 2 is the same as 5 to the power 3 minus 2, which will give me this answer, 5 to the power 1. Okay, so this is proven. What about the next one? am to the power of n equals to a to the power of n times n. Okay, so I'll just give you an example. Okay, 2 to the power of 3, and then I apply a power of 2 to this whole term. Okay, what do I get? 2 to the power of 3 is within the bracket. Okay, so within the bracket I have 2 times 2 times 2. If I have a square outside the bracket, this square, this power will actually be applied to every single term within the bracket when I expand it. So what this means is that this is actually 2 square times 2 square times 2 square. Okay, and if I apply rule 1, okay, because they are all the same base, okay, it's 2, 2, and 2. Okay, same base, 2, 2, and 2. I can combine them. The powers just add up, so it's 2 plus 2 plus 2. That will give me 2 to the power 6. Okay, so I will have 2 to the power 6 is the final answer. 6 is actually obtained from 3 times 2, right? Okay, so this 2 to the power of 3 to the power of 2 is actually the same as 2 to the power of 3 times 2. That will give me 6. Okay, so that's how I get rule 3. Rule 4 is just how do we actually prove it. It's actually just straightforward. We just apply factorization. Okay, the principle of taking out a common factor. Okay, in this case it is a power. We can take out a common power. Okay, so how do we prove am times bm equals to a times b bracket m? It's just that, let me just give you a reverse scenario, right? If I have open bracket 2 times 5 close bracket to the power 3, we have learned that in order to expand this bracket, the power will be applied to each of every single one of the terms within the bracket, right? So this, when I take away this bracket, I expand it, it will be 2 to the power 3 times 5 to the power 3. Right, so the reverse is also true. I repeat, the reverse is also true. If I have 2 to the power 3 times 5 to the power 3, it is the same as I'm taking out the power of 3, and then it is just 2 times 5 close bracket to the power 3. Okay, this is just a simple, straightforward application of taking out a common power. Okay, when I'm doing a factorization. Okay, now number 5, am divided by bm equals to a over b to the power of m. Okay, so what do? Same thing, I'm using the same principle of factorization. Okay, so let me just give you an example. Okay, the reverse example. If I have a bracket, open bracket, 6 over 2 close bracket square. Okay, what happens is that if I actually expand the bracket, okay, this power 2 will be applied to both the terms, so it will actually be 6 square over 2 square, right? The power 2, when I expand the bracket, it is the same as the power will be applied equally to both the numerators and the denominators. So it will be 6 square over 2 square, okay? And if I apply this 6 square over 2 square is actually when I have a fraction over this divide here. This line over in the fraction actually just means divide. So 6 square divided by 2 square, okay? So what I have now is, if I look at this, I have 6 over 2 bracket square is the same as 6 square over 2 square. So the reverse is also true. 6 square divided by 2 square equals to 6 over 2 square. Okay, so that's how I prove this. You can just see it as I'm just taking out the common factor 2 as well. Okay, and then whatever that remains within the bracket is just 6 divided by 2, which is 6 over 2. Okay, so it's just the same as part 4, whereby I'm just taking out a common factor of 2. Okay. For 6, how do I show that a to the power of 0 equals to 1? Okay, let me just give you an example. If I have 5 to the power of 3, I'm just using a hypothetical scenario. Okay, so this is purely hypothetical. So if I have 5 to the power of 3 divided by 5 to the power of 3, what does this mean? This actually means 5 to the power of 3 over 5 to the power of 3, right? This divide actually means over, means it's a fraction form. Okay, divide just means that it is in a fraction form. Okay, numerator divided by denominator, right? So 5 to the power of 3 divided by 5 to the power of 3 is the same as 5 times 5 times 5 divided by 5 times 5 times 5. Okay, if I cancel everything out, any number divided by itself is actually 1. So I get a 1 over here, right? Okay, then what about this? If I apply, so from here, okay, if I work this way, I will get 1. If I work another way, okay, I'm using the second formula. Okay, am divided by an is a to the power m minus n. So it is same base 5, so I can just combine the same base, and then because it's a divide, so the power is just minus away. So 3 minus 3 is actually 0. So 5 to the power of 3 minus 3 is actually 5 to the power of 0. Okay, so in other words, what I have is that 5 to the power of 0, this is actually equals to 5 to the power of 0, and this, okay, so this 5 to the power of 3 divided by 5 to the power of 3 is equals to 1, and it's also equals to 5 to the power of 0. So I can just say 5 to the power of 0 is the same as 1. Okay, so it's proven. What about this? Okay, number 7. Okay, part 1. A to the power minus n equals to 1 over a to the power of n. How do I prove this, right? So let's give you an example. If I have 1 over 4 square, okay, this is just another hypothetical. 1 over 4 square, what does this actually mean? It actually means I'm taking 1 divided by 4 square, right? So in the fraction, the divide line, okay, the line in the fraction actually refers to divide, the numerator divided by the denominator. So it's actually 1 divided by 4 square. I just express it in, instead of in the fraction form, I express it in the regular form. Okay, and what does this mean? If I apply this 1 is actually the same as 4 to the power of 0, right? Anything to the power of 0 equals to 1. Okay, apply rule 6. And what happens if I have 4 to the power of 0 divided by 4 square? I can apply rule 2, whereby it's the same base of 4. Okay, so I can combine them, and because it's a divide, the powers will minus away. So it's 4 to the power of 0 minus 2. Okay, because it is a divide here, so it will be 0 minus 2. Okay, that will give me 0 minus 2 is my 4 to the power of minus 2. Okay, 0 minus 2 is equals to minus 2. So if I look here, I have 1 over 4 square is actually equals to 4 to the power of minus 2. Correct? So I have effectively proven this, right? So 4 to the power of minus 2, I just flip it around. 4 to the power of minus 2 is actually equals to 1 over 4 square. Right? So the negative is just the same as taking the inverse, okay, of the original number, okay, which is 4 square in this case. Okay, so this is proven. Okay, 7 part 2, right? So what about previously they gave me the other expression as well. 1 over a to the power of minus n is actually the same as a to the power of n. Okay, previously, as you recall, I explained it in terms of because this negative represents the inverse of a to the power of n, if I'm taking 1 over actually also means the inverse. So if I'm taking the inverse of an inverse, the both inverses cancel out and I'm just left with the original a to the power of n. That's like a more sort of like a logical way to think about it. Mathematically, how do you actually prove it? Okay, so let me give you another example. Okay, hypothetical example: 1 over 3 to the power of minus 2. Okay, what does this actually mean? Okay, I already explained what a fraction means. It means divide. So 1 divided by 3 to the power of minus 2, right? This fraction here means divide. Using the same method, 1 is actually the same as 3 to the power of 0. Anything to the power of 0 is 1. So same base I can combine, same base of 3. So combine the power because it's a divide. So it's a minus. So 0 minus minus 2. Minus minus becomes plus. So it becomes 3 to the power of 0 plus 2. That will give me 3 squared. So in other words, I have proven 1 over 3 to the power of minus 2. Okay, it is the same as 3 squared. Correct? So the 1 over cancels away with the negative power to just give me the original 3 squared. Okay, so I've proven this. Okay, what about this? Number 8. A over b to the power of minus n equals to b over a to the power of n. Okay, so previously I explained it as this negative is an inverse. So if I take the inverse of whatever that's within the bracket, it's just I'm flipping it around, and a over b would flip around, becomes b over a. Right? So how do we derive that mathematically? Okay. Okay, let me just give you an example of 2 over 3 to the power of minus 2. Okay, let's just start with this. Okay, 2 over 3 to the power of minus 2. So what do we do here? We have learned that a to the power of minus n equals to 1 over a to the power n. The negative is, you can see as an inverse, or is a 1 over, right? So same thing, I take this negative sign here in negative 2, this negative sign here. Okay, I bring it on top. Okay, I extend this negative line to extend it fully, so it becomes, so I bring this negative sign up to the top, extend it fully, it becomes 1 over 2 over 3 squared. Correct? Also, this is actually this, okay, 1 over 2 over 3 squared. Okay, the negative becomes a longer line in the sense of a fraction. And what does this mean? This means it's actually 1 divided by the numerator divided by the denominator. Denominator is 2 over 3 squared. Okay. So what happens to this is that the square, when I expand this bracket, it will be applied to both the numerator and denominator, right? All the terms within the bracket. So it will be 1 divided by, okay, I expand this bracket, 2 squared over 3 squared. Okay. Here what I'm doing is that next step will be, if I have a divide, I can change it to a times, right? But in doing so, I flip the fraction, okay, that is being divided. So that you are dividing it by. So this fraction will be flipped around when I change it to times. Okay, so it will become 3 squared over 2 squared. Okay, and I can take out the common power of 2 and it becomes 3 over 2 squared. Right? So essentially what do I have? I have 2 over 3 to the power of minus 2, okay, equals to 3 over 2 to the power of 2. Right? So essentially I've proven it, right? Also 2 over 3 to the power of minus 2 is the same as 3 over 2 squared. Right? Whereby this negative, I can just take it as the inverse of whatever is in this bracket, and inverse means it just flips around. Okay, it's 1 over 2/3, which is the same as flipping the 2/3 around, which is 3 over 2 squared. Okay, so I've proven this. Okay, now what about number 9? Okay, if I have a to the power 1 over n, it's the same as I'm taking a root n of a. Okay, how do I prove this? Okay, this is a little bit more slightly more complicated, so you have to listen closely. Okay, right, so what I'm actually trying to do, okay, if I have let's say this is what I'm trying to do. Okay, I'm trying to show that this, let's say if I have square root of x, okay, instead of having it in the square root form or in the root form, I want to express it in the index form. Okay, and I want to find out what is it actually this square root over here, what it actually is in the index form, which is in the power form, what power it actually is. So if I have root x, what I want to do is I want to see what it actually is in the power form. So root x, what is it actually when I say x to the power of something? Okay, what is this something? This root, what is this something? Okay, what is its equivalent value when it is in the form of a power? So what I do is the rest of the equation, I just put it as I apply a square to this root x equals to x. Okay, and the rest of the equation will be same thing. I apply this square equals to x on both sides, right? So I'm trying to see what they actually what actually is the equivalent value, okay, between what's highlighted on the left and highlighted on the right. So what I do is I'll just do some manipulation on the right hand side, okay, this portion here, okay, this right hand side, okay. So if I have x to the power a bracket square equals to x, okay, I'll notice that based on the rule above, if I have am to the power of n, is actually a to the power of m times n. So when I take away this bracket, it's actually x to the power of a times 2, which is 2a, okay, and x is the same as x to the power of 1, right? So if I have x equals to the power of 2a equals to x to the power of 1, because the base is the same, okay, and they're both equal to each other, so I can just say that the power is the same as well. Okay, so here I'm just comparing. Okay, I repeat, I'm just comparing what's on the left hand side and the right hand side. If I have x to the power of 2a on the left hand side equals to x to the power of 1 on the right hand side, if the base is the same, I can say that the power is simply the same, right? Because otherwise, how are they going to be the same? Okay, the powers have to be the same. So 2a actually equals to 1. Okay, I'm saying the powers 2a equals to 1. Okay, and just some simple algebra, a equals to half, right? Bring the 2 over, becomes divide, so a equals to 1 over 2. So what I do is, because here I have a equals to 1 over 2, right? And here there's an a over here, correct? If you can see, there's an a over here. Okay, so I will sub this a into here. So basically what I will get is x to the power of half to the power of square equals to x. Okay, I sub the a back into the original. So x to the power of half to the power of 2 equals to x. So here, once again, I can see that if I compare root, everything else is the same. So I'm comparing this x to the power of half with root x. Right, everything else is the same. There's a bracket, there's a square, there's an x. So x, this root x here, when I express it in the power form, is actually x to the power of half. Okay, so I compare these two, and then what I'll get is x to the power of half equals to root x. Okay, that's how I prove it. So half actually means this number here will be the square root, because this number here is 2, so it's square root. Right? And 1 over just means that if I have x to the power of 1 over something, the 1 over represents is a root. And this number at the bottom here will tell me the degree of the root. Okay, in this case it's 2, so it's a square root. So I've proven this formula. Okay, number 10. Okay, last but not least. Okay, so if this is the formula, that was the rule that was given. Okay, a to the power of m over n equals to, okay, square root, not square root, okay, root n of a to the power of m, or I can have the m within the bracket, okay, within the root itself, such that it is root n of a to the power of m. So how did I explain it just now, if you can recall, is that this a to the power of m over n, because it is 1 over n, okay, so as mentioned in 9, okay, a to the power 1 over n is the same as a root n. So this 1 over n here, okay, actually will give me a root n, okay, and then this value of m is just a power, right, a to the power of m. So this whole thing will just be have a power m applied, and then what else is that this m, the mathematical value is the same, be it outside of the bracket or if I put it within the root n. Okay, so this power m is the same if I put it on the outside of this root n, or if I put it within the root n. Right, it's the same value. So mathematically, how do we derive that? Okay, so here I'll just give you a hypothetical number, which is 8 2/3. Okay, so I'm starting on 8 2 third. Okay, how do I manipulate this? So as you can recall, if I have 8 to the power of 2 third, it is actually the same as, this 2 third power is the same as 2 times 1 third, correct? 2 times 1 third will give me 2 third, right? So 8 to the power of 2 third is the same as 8 to the power of 2 times 1 third, right? Because 2 third is the same as 2 times 1 third. Okay, or alternatively, I can just flip it around. 1 third times 2 also gives me 2 third, right? So 2 third I can say is 2 times 1 third, or I can also say that it's 1 third times 2. Doesn't matter which way I put it. If I multiply the both of them together, they will both give me 2 third. Okay, it's just a matter of which comes first. So now what I can do is, if I have 8 to the power of 2 times 1 third, if I apply the previous rule, okay, which is am to the power of n, okay, to the power of n equals to, okay, this is the rule, a to the power of m times n. Okay, so if I have 8 to the power of 2 times 1 third is the same as, I can just put one of them as a power, okay, on the outside. So I can say that it's 8 squared to the power of 1 third. Alright. So on the other side, I can also, because 1 third comes first, so I can just say that it's the same as 8 to the power of 1 third to the power of 2. Right. So I can, because it is the powers are multiplied by each other, I can just simply, okay, say that it is simply one of them to the power of the other. Okay, based on this rule over here. So 8 to the power of 2 times 1 third is the same as 8 squared to the power of 1 third. And 8 to the power of 1 third times 2 is the same as 8 to the power of 1 third. And then I apply a square, the power of square to this whole thing. Right, so I will have this or this. Okay, and what happens here is that if I have a power of 1 third, yeah, it just means that it is the cube root. Right, 1 to the power of 1 third, because to the power of 1 over means that it's a root, and the number below tells me the degree of the root. In this case is 3, so it's a cube root. So it is a cube root of 8 squared. Right, here it will be 8 to the power of 1 third is within the bracket, so the cube root of this 8, okay, will be within the bracket. Okay, and then the square is applied to this whole cube root of it. Right, so 8 1 third is the same as cube root of 8, and the square is applied to the whole cube root of it. Right, so what I do have is that I can say that this 8, okay, this cube root of 8 square is the same as, I take the cube root of 8 and I just square it. Right, these two have the same values. Okay, so that's why I can say that, okay, this, okay, is over here. Okay, I cube root the 8 square, okay, has the same value as if I square the cube root of it. Right, so these two are the equivalent value. Okay, they actually have the same mathematical value. So as you can see, it doesn't matter whether this square over here is outside of the bracket or is within the root itself. Okay, they both have the same value, and of course they are equals to 8 to the power of 2 third. Right, because that's the starting point that I have. Right, the starting point is I started working from 8 to the power of 2 third. Right, for both situations. Right, so they are both equals to 8 to the power of 2 third. Okay, so yeah, with that I have completed proving, okay, all of the rules.